Hi, let's start learning something new. So, just overall for this week, we will start with BJT. So, open your textbook, chapter 5. So, I will cover a little bit of 5.2, 5.3, and 5.4. Then we will move to chapter 6. Okay, so let's go for this week. Hey, so for the first week of this semester, we're gonna try to review a little bit about BJT, especially just the DC part of BJT. So what is BJT? Bipolar junction transistor. Here is two common examples of BJT. I have the NPN and the PNP. So it's just based on how you dope the semiconductor material, either with hole or electrons. The characteristic of BJT lay on the junction between the N and the P, or the P and the N. So when you perform DC analysis of BJT, you actually perform the analysis on the junction of the BJT. So two main type BJT, NPN and PNP. Both of them all have three pins: a collector, a base, and an emitter. However, the current flow differently. So for NPN, current from collector and base coming in, then coming out from emitter. But it is reversed for PNP. So current coming into the emitter and come out from the base and the collector. So if you think about it this way, for NPN, the emitter emit hole instead of electron, so you have a positive current flowing out emitter. But for PNP, the emitter emits electrons, so you have a negative current. Okay. I also give the set of equation here that you guys can use later. Common emitter circuit of BJT. So in this diagram, you can see we have two different diagrams here, and we have a BJT in the middle. Okay, the emitter terminal is obviously ground at ground potential. Okay, so the figure A here shows a common emitter circuit with an NPN transistor. So this diagram is NPN. You can see the current flow out to the emitter side. And B is the DC equivalent of this circuit. Okay, so every time you see an NPN BJT, you can immediately convert that into a 3-port block diagram like this and use this component instead. It will help you analyze the DC circuit a little bit easier. So we will assume that the BE junction, is here, is forward bias. So that's why we have this diode. We have this diode right here. So the voltage drop across the junction is the turn on voltage, which also is noted as VBE on. Okay, and the current, which is the base current, this base current and the collector current is dependent. So precisely, the collector current IC is dependent on the base current. Okay, so by a factor of beta, and you can find this number based on the data sheet, assuming it's in the forward bias mode. Okay, so now we have the equation for the base current, and how do we get it? So just basic electronics again. So we have current flowing through the base. Okay, there's a resistance of the base, which is RB. The current flowing through the base I will call it IB. So Ohm's law, we will have the voltage across the base. I will say VB over RB will give you the value of base current. So to dissect the voltage, the base voltage, basically you have to see where's the two node. The first node will be VBB, right? The second node is VBE. Okay. So when you have the two nodes, VBB and VBE, you can just subtract VBB for VBE on to get the voltage across the base. So here is our equation for the base current. In this equation, you can see that so obviously when VBB is larger than the turn-on voltage VBE on, you will have a positive current, so current will be allowed to flow through here. But remember, now you have a diode right here, right? A diode means you can allow current to flow one way but not the other way. So when you have VBB less than VBE on, you don't have a negative current. You have the current IB, the base current will come to zero. So it's the cutoff. Okay. So how about the current of the how about the collector current? So basically it's just a fact, like you just multiply the base current for beta. So commonly you can find this beta number in your data sheet, 100, 200. So just look it up, and usually in questions of exercise or exam or homeworks, it will be given. And finally, how do I determine the VCE, or the current emitter voltage? So first, let's look at this diagram first. So you can, from here, you can easily see that VCC, okay, which is the source current, the source voltage, is equal to the voltage across this collector resistor RC right here, plus this voltage. So the voltage across here and this voltage, you add them together, you have VCC. This is obvious, right? So now you can also write the voltage across this resistor as IC multiplied by RC is Ohm's law. Okay. So that way now you can just flip the two term over. So now you can have VC equal VCC minus IC multiplied by RC. How about the power? So assuming you all know that power equal current multiplied by voltage, P equal IB. So the power dissipated in the transistor, and I will note that as the P transistor, which is power of the whole transistor here, it will be the total power dissipated at the base and at the collector. Okay, so on the base you can have basically IB current multiplied by VBE on, okay, and then you can have IC current multiplied by VCE. Okay, so add them together, you can have the total power dissipated in the transistor. However, commonly the value IC, which is the collector current, is a lot larger than the base current, and also the collector emitter voltage is also larger than base emitter voltage or the turn-on voltage. Therefore, you can assume that this value here is a lot larger than this. Then a good estimate is you can just take this one out, assume it to be 0, and just calculate just estimate the power dissipated in the transistor to be the power of the collector. So let's work together through an exercise. So given the circuit here, it's exactly the circuit that we have in the previous slide. However, I just give you a few parameters so we can work this problem out together. So what I want you to do is I want you to calculate the base current, the collector current, the emitter current, the collector emitter voltage, or the voltage across the collector and emitter, okay? And finally, calculate the dissipated power throughout the transistor, okay? You are given some information, some information like the base emitter voltage will be 0.7, and you probably will see this number a lot in the future. And lastly, the beta factor is 200. Okay, so if you need some time, pause the video for a few minutes and work the problem out by yourself, and then you can continue to play the video. So first of all, we'll try to calculate IB, which is your base current. So given the equation from previous slide, okay, you plug the number in, you can have IB to be 15 microampere. Next, IC is a lot easier because IC is dependent on IB, which this beta factor. So you just multiply IB for 200 and you can have the answer is 3 milliampere. Next, your emitter current. First of all, emitter current, technically you can use KCL, which is curve current load. So current coming in equal to current coming out. Okay, so current coming in here is IC and IB, right? Therefore, you can say IE equal to IC plus IB. But also IC is also equal to beta IB. Okay, so you can have another equation that you can use, and it's always true, is IE will be equal to beta plus 1 multiplied by IB. Therefore, I will have my emitter current to be 3.02 milliamperes. So a little bit higher than this. Next, I will calculate the voltage across collector and emitter. Okay, so the voltage across emitter and collector is equal to this voltage minus the voltage across this one, which is IC. I mean, across the collector resistance. So I can have 10 minus IC multiplied by RC, which is 3 multiplied by 2, can have 4 volt. Okay. And finally, plug in the equation for dissipated power, which is IB VB. Okay, multiply that two number, then plus. So basically, this is the power coming from the base, the power coming from the collector. Add those two numbers together, you can have the final 12.01 milliwatts. However, you can also estimate. Okay, you use some estimation. This number is relatively small, so you can just ignore the whole thing and write down the answer as 12 milliwatts. So it's a pretty good approximation. So is there any standard approach for problems? So to solve a problem in DC analysis of BJT. So I put together a few steps here. So first, assume that the transistor is biased. The transistor bias is in forward active mode. Okay. Therefore, you can have VBE equal VBE on. The base current is larger than 0, so it's not cut off. And then you have the collector current is dependent on the base current. with a factor, then this is a given factor better. So then you analyze the linear circuit. Okay, just a bunch of Ohm's law, K-curve, nothing difficult. Then you evaluate the resulting state of the transistor. So now you see if the VCE is larger than the saturation VCE. Your assumption is correct. If your base current is less than 0, the transistor is likely in cutoff. Or if your VCE is less than 0, the transistor is likely in saturation. So we will cover this in the next lecture video about different mode of operation. And finally, if the initial assumption is incorrect, you can make new assumption, okay, and return to step 2. Okay, so just keep repeating the loop. Okay, so next time we will basically study about load line and also different mode of operation and different application of BJT, such as amplifier and biasing. I recommend you go ahead and read your textbook. We are at the chapter 2, section 5.2 of the textbook, and I do recommend you guys to go and do the optional practice of example 5.5, and I'll see you guys next time. Bye bye.